Okay, so let's start. Well, last time, yeah.
Just.
Yeah. Hello.
Hi.
Bless you.
Yeah. Last time, we defined elliptic functions as a meromorphic function on the curve, or sorry, or as a doubly periodic meromorphic function on an elliptic on convex plane. And from we defined, we constructed two examples. Heat function, this is it, and Jacobi's SN. And we proved several fundamental theorems of elliptic functions. One is that holomorphic elliptic function is just a constant. So non-trivial elliptic functions inevitably have poles. And the second theorem was the sum of residues is equal to zero. Sum of zero residues in one periodic parallelogram is zero. And as a corollary, there is no elliptic function with only one simple pole. And we named the number of poles in a periodic parallelogram order of this elliptic function. And the order is very important characteristics of an elliptic function. And okay, as you see, the number of solutions of this equation in one periodic parallelogram is equal to this order. And the last theorem we proved is that sum of solutions of this equation and sum of poles of this elliptic function is equal up to this linear combination of integral linear combination of periods. So today we are going to define Weierstrass P function using these properties of elliptic functions. Okay, let's recall that holomorphic elliptic function is compact, and there is no elliptic function of order 1. So the simplest non-trivial elliptic function is of order 2, which means that in this period parallelogram, there is one double pole, or there are two simple poles. And our P function, which we defined last time, was this type of elliptic function. And Sn has two simple poles in one parallelogram. So actually, this double pole corresponds to the fact that infinity is a branch point of this Riemann surface. Well, yeah, today we construct this P function as a series, not starting from the Riemann surface or this elliptic integral, but directly construct the P function. To do this, we take two complex numbers which are linearly independent of R. So this is a parallelogram, which is not degenerate. And gamma is, as usual, the lattice, period lattice. Then what we are going to do, or what we want, is for some simple elliptic function with double poles at gamma, which means here, here. So on these lattice points. So what is well, assume that an elliptic function has a pole at gamma, or lattice points. Then if the pole is over the n, by definition it has such a lower expansion, starting from n. So this part does not have any other poles on the complex plane. So it might be expected that such combination, or sum of all these sum over all lattice points, is an elliptic function. The problem is, of course, the convergence. This is our infinite sum. So whether it represents a function depends on convergence of this sum. Actually, it is true for n bigger than 3. the first theorem today is that for n, which is bigger than 2, sorry, this series converges absolutely and uniformly on any compact set.
Sorry, excuse me, Takashi. You mean that it should say 2?
Well, n cannot be 2.
Okay, okay, understand. And so I heard you said 2. Okay.
So if n is bigger than 2, so n is bigger than 2. And well, as I said, it has a pole at each point, lattice point over the n, and this is elliptic function. And actually, this function has a good parity. When n is even, it is an even function, and n is odd, then odd function. Well, the proof is a sort of exercise for our students, but let me tell you details. First, take any compact sets. This is it, which does not contain lattice points. And take R, which is so large that this disk contains this compact set. Since compact set is bounded closed set, there should be some big number R. And let's consider the partial sum.
Takashi, can I just ask another question? Isn't it?
Yes.
We require that this doesn't include 0, right?
Which?
Because if it's 0, we get 1 over u cubed, and it doesn't converge uniformly. We must have m1, m2 are not equal to 0.
It is. You are too fast.
No, it's just a question.
P function, then we should exclude 0.
It was not a clever question. It was an innocent question, because I noticed that anyway. So you're not excluding 0 at this moment?
No.
Okay.
No.
Sorry.
So, well, if n is not less than 3, then construction is much easier than P function. But still, for the proof of the convergence, we should exclude several points. So, yeah, DO2R is a circle like this. And we exclude all lattice points in this disk. So, of course, if we add several terms to this sum, then we recover this series. But for the proof of convergence, we don't need those finite terms. So let's prove that this series converges absolutely and uniformly on this smaller disk. So first note that each term can be written like this. And this is a easy.
Takashi, it
Yes.
cannot, it's not true if omega is 0.
Yeah, but we are assuming that omega is outside of this large disk.
Ah, God, of course, I'm
So you don't have to worry about.
Of course, I'm so sorry.
Division by 0.
Yeah, excuse me, I'm sorry. This is the point I missed, sorry.
Then, well, yeah, this part is bounded by M because the absolute value of U is less than R and absolute value of omega is larger than 2R. So U over omega is, well, yeah, this is probably, this is a 1/2, right? So, which means that this is larger than 1/2. Am I right? Yeah.
Yeah, it's right, but it's also less than 1, isn't it?
So actually, we can take M over to N as this bound, but now it is not. And then the concrete value is not very important. We can bound this factor by some constant, which does not depend on omega. And so this means that this sum so sorry, I forgot to put parts. This absolute value of this term is less than M. This is less than, well, M omega, right? Yeah, from this and this. And well, so we can pull this factor out of this sum, and the
No, but M depends on N, sorry, Takashi. M,
yeah, it depends on N, but here we are fixing N. So
sorry, yeah.
That doesn't matter. Yeah. And we can prove that, yeah, later we prove that this sum converges. Well, actually, this sum is larger than this sum, but it doesn't matter. So by Weierstrass M test, Majoran test, this converges absolutely and more uniform because this estimate E does not depend on U. Here, there is no U. So yeah, then that's what we want. And the proof of this convergence is elementary. First, let's take some number R, small r, which satisfies this property. The circle disk with radius r is included in this the smallest parallelogram around 0. So this parallelogram is, well, in this larger picture, it's here. And if we multiply some number k, for example, 2, then the parallelogram extends to, enlarged to this larger parallelogram. And the circle with radius 2r is included in this parallelogram. Okay, so pk is a parallelogram with these vertices. Then, well, let's estimate this sum. This sum is decomposed in this way. So first take sum over each parallelogram, each boundary of parallelograms, and then sum over k. Then, well, let's see. Take this sum, partial sum. On this large parallelogram, there are 8k lattice points. You see, for example, here on this parallelogram, we have on each edge we have 1, 2, 3, 4 lattice points. Well, yeah, so we have 16. On this parallelogram, we have 1, 2, 3, 4, 5, 6 times 4 means 24, and so on. And each term is because of this, each term is bounded by this. So we have this inequality, namely this one. So recall that R is fixed here, and N is also constant. And we have sum over K. And such sum converges when N minus 1 is larger than, strictly larger than 1. Namely, N is strictly larger than 2. So we proved this lemma, and yeah, we proved this statement. Now, let's prove that in this series defines an elliptic function, namely meromorphic function, which is periodic. But because this series converges absolutely and uniformly on any compact set, Weierstrass theorem for convergence of holomorphic function or convergence of a series of homomorphic functions says that f is homomorphic on the complex plane except at gammas. And at gamma, at each lattice point, it has such a term around omega, so it has a pole of order n. So it is a meromorphic function. And periodicity is, something's wrong, sorry. Oh. Just a moment. So Fn is a meromorphic function, and periodicity is almost evident because of this sum, Fn of u plus omega is Fn of u. Because if we shift this argument, then we can shift M1 and M2 by these numbers, and the sum remains the same. So it is a doubly periodic meromorphic function, which means that it is an elliptic function. So we have constructed some elliptic function, and for later use, let's prove this parity. And this is also simple because, well, just substitute minus u to u. This is it. And replace omega by minus omega. Then we have such a summand, and this is equal to this. And well, yeah, this does not depend on omega prime, so we have this. So when n is even, then it is an even function. If it's odd, n is odd, then it is an odd function. So this is the end of the proof. So we obtained some elliptic function of order n, but n is larger than 2. We want, as we discussed, we want an elliptic function of order 2, not 3. But unfortunately, this construction, which we proved here, this construction does not work for 2 because this sum diverges, as in, well, yeah, here we use the fact that this sum converges when n is larger than 2. But when n is equal to 2, then this is so-called harmonic sum, harmonic series. So it is infinity. So actually, this construction does not work. So we have to somehow correct summand to get a finite convergent series, which is this. So the theorem is that if we subtract something from this summand, except at 0, then this series converges absolutely and uniformly, well, shortly speaking, this defines a meromorphic function. And this is actually periodic and even. And as you see, the order of poles is 2. So this series defines an elliptic function of order 2, which is called Weierstrass-P function. So, but a priori, this series does not seem so periodic because 0 is excluded from this sum. So how to prove this? Well, in order to prove this theorem, we proved the convergence of this simpler sum for n is equal to 3. As we know, this series defines an elliptic function. Okay, so what exclude this first term, and integrate this from 0 to u. From 0 to u. But of course, the contour, integration contour should avoid lattice points. Well, yeah, this integral does not depend on gamma because this sum does not have a residue. So if we change gamma from this to this, we pick up residue at this lattice points, but at each lattice point, this series does not have a residue. So we do not have to specify their integration contour concretely. Okay, so as we saw, this sum is absolute and uniformly convergent, so we can change the order of sum and integration like this, and this is equal to okay, this. It is a exercise for high school students. High school, yeah, probably. Well, with my -1/2. So the series for P function is like this. So we get this part by integrating F3 like that. And yeah, Pu is this function. We know that this is a meromorphic function because F and of course 1/v cube is a meromorphic function. And of course, this is a meromorphic function. So this defines, or this series defines a meromorphic function with second order poles at gamma. Moreover, derivative of this function is of course F3. Because, well, derivative of this part is -2 times F3 plus derivative of this part, which cancels with derivative of this part. So, well, so we want periodicity of the function, but before that, first let's prove evenness, parity. Namely, this equal to this. And this is as easy as the proof of the parity of this series. Just put -u here. This is the definition. And well, yeah, this is equal to this. And just replace this by -omega prime. Of course, this is also minus. Then, well, yeah, it becomes just P function. So P function is an even function. And lastly, we prove the periodicity. First, because P prime is essentially F3, we know that it is a periodic function, which means that P of u plus omega 1 and P of u plus omega 2 is equal to Pu up to constant. Let's prove that they are 0. How to do that? Well, just put minus omega 1 omega 2 over 2. Then this part becomes omega I over 2. And this is, of course, this. And C1 and C2 are differences of these values of P functions, but we know that it is even, P is even, so they are equal, which means that Ci is 0, namely it is periodic. Thus we have constructed an even elliptic function with poles of order 2 at each lattice points. Okay? So, construction or series expansion is not very beautiful, simple as this, but it doesn't matter. What is more important is a differential equation, which P function satisfies. Well, let's first expand this P function at 0. Of course, the singular part, the principal part is 1 over u squared, and this part is homomorphic at 0. So we have a Taylor expansion for this part, and this is a principal part. And this is a this is the Taylor formula. The coefficient for u to n is equal to this value, this derivative. And for example, when n is equal to 0, C0, it is 0 because we do not have this derivative. And u is 0. Then, of course, each summand vanishes, so it is 0. When n is not equal to 0, then, yeah, first we differentiate each summand. And this part vanishes at once, and we have something like this, minus 2, minus 3, 2, minus 2, and so for 1 over 2. And this part cancels with this, and also this is minus 1. And yeah, we have actually even number of minuses, so there is no sign here, and from this part we get this. So yeah, each coefficient can be expressed as a sum over lattice points. Well, for later use, we multiply some very strange numbers, 20 and 28 to C2 and C4. And we call this G2 and this G3. Why 20 and why 28? I shall explain now. Well, so we have this Laurent expansion, and of course, by differentiating, we get this Laurent expression, Laurent expansion of P prime. So from this expression, we have such. Yeah, the first term is 4 over u to 6. And well, the second term comes from where? Yeah, from this product. And this comes from product of these two. Of course, we need to multiply 2. And the rest is already holomorphic. Well, cube of this P is like this. Cube times minus 4, like this. And this is the same as this. Just we multiplied G2. And sum up these 3 functions. What happens? Well, this cancels. This cancels. And we have minus G3 on the right side, plus some function of order u. Okay. But P prime is a negative function, so square of P prime is of course a negative function. Well, this is I forgot. So this is of course our elliptic function, and this too. So this is an elliptic function, and the possible poles sit at gamma. But the left-hand side is holomorphic at 0, which means holomorphic at each lattice point, even because this has period gamma, elliptic function. what does this mean? This is an Elliptic function, and poles, possible poles exist only at gamma, but there is no poles at gamma. Therefore, the left-hand side here is an Elliptic function without poles. And the first theorem we proved last time says that this is a constant. And our constant should be this term. Because this part becomes 0 at 0. What we obtained is this differential equation for P prime. Okay. Yeah, which means that dp over du is the square root of the right hand side. Namely, u is the integral of du, and this is equal to such an integral. Namely, u is expressed as an integral of this one form from infinity. Why infinity? Because, well, we have to integrate this one form from a point where u is equal to 0. U is equal to 0 means P is an infinity, the infinity. And here we have U, which means that we have to integrate this one form from infinity to P of U. So this is what we wanted. I mean, we defined P function last time. By this. Inverse function of this Abelian map. And this is exactly this. Actually, we can prove that such a map from U to PU and P prime U defines the inverse map of Abelian map. Abelian map is like this. And yeah, P0 should be in this context is infinity. One. First, yeah, this pair belongs to this elliptic curve. Why? Because P prime square satisfies this differential equation. Okay. And what we have to prove is that it actually gives an inverse of this map, or yeah, we should prove bijectivity of this map. Well, yeah, this is actually an exercise. I didn't expect that we can reach this point. So I have not yet put the homework assignment on the website. But yeah, please try this later. And the other very good property of this P function is that any elliptic function is expressed in terms of P and P prime. Like this. Or this is also an exercise program, but yeah, the idea of the proof is like this. First, we decompose elliptic function into two parts, even part and odd part. And if f is even, so without this part, we can express it by the P function, as a rational function of P function. By matching zeros and poles. And if f is odd, then P prime of f is an even elliptic function. So this should be expressed in terms of P, like this. This is this part. So in terms of P, we get every elliptic function. which means that meromorphic function on this elliptic curve is expressed as a rational function of Z and W, which is quite non-trivial from the first definition, because f is defined to be just meromorphic function. But from this, we get rational function. Actually, we have a similar, well, yeah, phenomena of P1. If f is a meromorphic function on P1, then f is a rational function. Well, I think we proved this some time ago. Yeah. So if f is meromorphic, then we have principal part f has such an expression. This is principal part, and there is a homomorphic part. Let's call this pi, and this is just a rational function, right? And yeah, at infinity we have since this is meromorphic even at infinity, we have such an expression at infinity. Let's call this P0. Then, if we subtract all singular parts at poles, then it is homomorphic function on P1, which is just constant because of Liouville theorem. Therefore, meromorphic function on P1 is expressed as the sum of polynomial and certain sum of rational functions plus constant, which means that this is rational. So this is the theorem for genus 0 Riemann surface. This exercise program is for genus 1 Riemann surface. And actually this is true even for any Riemann surface of genus G. Namely, we can express any meromorphic function on Riemann surface, compact Riemann surface of genus G as a certain rational function or of certain variables, which of course I cannot prove here. Okay. Okay. Now, yeah. So the rest is that, yeah, the last property I want to show you is the addition formula for the P function. So we know that another elliptic function has certain addition formula. P function also has an addition formula, which is like this. Of course, you might complain, well, yeah. So. Here, U3 is related to U1, U2, like this. So by the parity of this P function, this is P prime of U1 plus U2. This is P of U1 plus U2. So this relation is the relation among values at U1, U2, and U1 plus U2. So it is called addition formula. So you might complain that this formula does not have an expression like this. Well, actually, we can do this by using this differential equation. So we can at least write P prime here and there in terms of P of U1 plus U2, U2, P of U1. But of course, it becomes very messy expression. So first, let us prove this simple form. And later we mentioned about this simpler expression. But actually, we should not expect too simple expression because, for example, for sine, we call this addition formula for sine. But this actually contains cosine with sines. If we want to kill this cosine, we must use this formula. But of course, we do not want root or and so on. So yeah, such an expression actually corresponds to this kind of simple expression. Okay. So well, yeah, time is almost up. So let's prove this addition formula next time. Yeah. So what we did today is the construction of p function and p function and which is an even function of order 2 and satisfies this fundamental differential equation, which states that this is an this gives an inverse map of Abel-Jacobi map. Okay, any questions?
I have one question, but not according to this lecture. Could you please send your presentations with these, your notes?
Okay.
I mean, to everyone.
So then let's stop and